would use this if you really come to understand what's happening. The equation deals with this part up here. Mole ratios come based on, and it could be, just because it shows you this bridge, you could be talking about just the reactants or just the products. It doesn't have to be reactants to products or products to reactants. The idea is you have one substance and then another substance. So it could be, for example, and somebody tell me how you would balance this.
You put 2 on the hydrogen.
Okay, well you would see that there's 2 oxygens, so I needed 2 here to give me 2 oxygens over here, and that looks backwards and says, oh, I gotta get 2 hydrogen. So you could be saying, I start with so many, they can tell you how many moles of hydrogen you have, and they want to know how many moles of oxygen you get. So it wouldn't have to be converted from here to here or here to here. It could be both along the same side. You could have 2 products as well. The idea is that you have, these mole ratios are determined by the balanced chemical reaction. So, and they may give you the mass, or they may give you the number of moles of oxygen, and I ask you how many grams of water. So then you're starting here and going like that. Does this, if you guys look this much, I think it should really help. In the past, my classes said it really helps. And this is another way to look at what's happening. Molar mass goes from moles to grams to mole. The mole ratio comes from the equation. And that's right here. All right, and I would have this. Now, this is mole ratio. This is the actual one, not one I built, but
So this is work to do?
this is work to do for next week. And it's not a lot to do. It's pretty simple. It's balancing equations, but when you do your work, be sure you show it in stages. So for all of the work, you're going to be just dealing with moles to moles, which is looking at the reaction, so it's pretty straightforward. Number 4, suppose 4 grams of hydrogen were used. How many grams of water would be produced? You have to start with, it says 4 grams of hydrogen times, well, H2, each one is 1.008. So since you have H2, you have 2 atoms of hydrogen, right? So it'll be 2.016 grams of hydrogen per 1. And isn't it funny how they abbreviate it typically with MOL? Now I've gone from grams of hydrogen to moles of hydrogen, and they want to know, I don't want to do this whole thing unless you get the idea, how many grams of water. Well, we got to do something that converts moles of hydrogen to moles of water, right? And this is determined by your equation, this mole ratio. And then you got to convert moles of water to grams of water, and this comes from the molar mass. 2 hydrogen atoms, 1 oxygen atom, look at your periodic table, add up all the numbers, the atomic mass. If you have a mole, the atomic mass is going to be in grams instead of numbers of nuclei. So, why don't we briefly go through, I don't think that'll take that long, but why don't we briefly go through, are there any questions about what I put up there? Is it okay with that?
I think so. So like, for the part that you would it be like 2 to 2?
Yeah, it turned out to be 2 to 2, right.
So, actually,
And that 1 mole you got is going to be about 18 grams roughly of water per mole of water. So, I think it's about 36 grams of water roughly, to be more specific. So, balancing chemical reactions. In this case, the silver plus H2 answer Can you tell? What was by itself on the left side?
The
Ag, which is silver. What's by itself on the right side? Okay, so hydrogen, silver kicked hydrogen out of its bond from silver and took over. Yeah, it's what? Single replacement. If they exchange places, then it's double. If they're both bonded to something. So the reactants, you know what that is. That's what on the left side, the products are on the right side, where there are points. When you talk about subscripts and coefficients, counting the atoms tells you, you can figure it out from the reaction. So for example, with subscripts, H2O says you have 2 atoms of hydrogen and 1 atom of oxygen. You don't say H2O1, you don't have to do it, just like you coefficient, you have to put it above it. It's just like in algebra, we write x, x2, but we don't have to write next to the 1. We don't have to say 1x. The coefficient isn't written, in algebra, you don't have to say. Same kind of thing happens with both the chemical equations and the molecules involved. Okay, now, the coefficient shows how many molecules there are in a particular chemical. So we look at, on the right side, 2 molecules of water. The H2O tells you that each molecule has 2 atoms of hydrogen, 1 atom of oxygen. That's what the subscripts tell you. We already talked about this. If you look at this example, the law of conservation of mass, okay, in the chemical reaction, matter is not created or destroyed. So if I have, on the left side, 4 hydrogen and 2 oxygen, on the right side, you better have 4 hydrogen and 2 oxygen atoms. We're not talking about nuclear reactions where 1 atom can be changed into a different kind of atom. If an equation follows the Bayes law of conservation of mass, we call it being balanced. So if you just write that H2 plus O2 equals H2O, it's not balanced yet. And you'll notice there's a problem because before I put those 2 green 2s, the number of oxygen atoms on each side was not the same. That was what caused the problem, right? And here's methane plus oxygen forming carbon dioxide with water. What kind of reaction is that?
Double replacement?
It's oxidation. Whenever you see oxygen on the left side, a carbohydrate of some form plus oxygen, it needs oxygen to happen. Either it's forming carbon dioxide and water, it's oxidation. Photosynthesis is like reverse, going from right to left. You start with carbon dioxide and water, you form glucose, which is a carbohydrate, plus oxygen. Remember, there might be oxygen atoms in here, and you use that to figure out what number to put in here. If I got a number like 2.5, I multiply the whole thing by 2, so this becomes 5 when you gets doubled. So, if you look at what we have, we've got 1 carbon, 1, 2, 3 oxygen, 2 oxygens, 4 hydrogen, 2 hydrogens. So it's not balanced, right? Yeah. When I change it to this where it's balanced, now you can see that I've got 4 oxygen, 1, 2, 3, 4 oxygen, 4 hydrogen, 4 hydrogen, it's all balanced. So that's all we mean by conservation of mass. The number of individual atoms is the same on both sides. You don't gain or lose mass. Are all protons and neutrons the same size? You just guessing or confident in that?
I'm not confident.
They are not all the same size. But as you get larger molecules the protein, then neutrons and protons tend to get slightly bigger atoms. It's like there's additional energy needed to hold them all together. So anyway, you can see that it's the same. This is one of the they produce for us. Matter cannot be created or destroyed, substance cannot be added, removed, or changed. You can't change the substance, because if you do, you're changing the substance. Now you can change, put a coefficient in front of these. I can't change these. That subscript has to stay the same. You only change the coefficients, and they go in the coefficient always goes in front, not in the middle somewhere, of course. Try balancing the bigger molecules first. In general, not always true, but you want to look where there's a change, and deal with the molecule first before you deal with individual elements. And polyatomic ions are treated as one unit. Here's one more. N2H2. Nitrogen gas with hydrogen gas forms ammonia gas. But you can see we've got 2 nitrogen on the left side, 1 on the right. We've got 2 hydrogen on the left side, 3 hydrogen on the right. That's not balanced. So if we start by writing down, that's what we have on the left side. On the right side, so I'm going to put a 2 in front of the ammonia. I'll try to fix this up a little bit so it'll work right. And that's on the right side, so that should double those 2 terms. Instead of 1 and 3, it's now 2 and 6 because I put a 2 in front. Now I look back on the left side, what do I have to change? Put a 3 in front of the hydrogen, it makes that 6, and now it's balanced. You don't have to write one of these little tables. I never really do that, but oxidation reduction reactions called redox, reduction, oxidation, are really complicated, messy, not easy. They have a whole step method to go through to do it. It's really complex. Second semester at some point you will probably do that. Let's do another one. Well, whoops, yeah, I had trouble. It was already done with, and I tried to fix it. I kind of gave up on this one. So what we start with, before the 2 and the 3 in red there, you have 1 potassium, 1 chlorine, and 3 oxygen. On the right side, you get 1 potassium, 1 chlorine, 2 oxygen. Right? That's not balanced. You ignore the 2 and the 3 there. So we say, well, if I put a 3, that doesn't really take care of it. Let's put a 3 right here because now, I could do 3 halves, but we don't want to do that. So then I put both the 3 and the 2. Come on. There's the 2. Let's do it again. Okay. There it is. Well, that wasn't very clear. Let's try this one. If we look at what we had before, that last one is a polyatomic ion, sulfate, SO4. We have 1 sulfate on the left, we have 3 of them on the right. So you can see things are balanced. When you deal with a polyatomic ion, it almost always, not always, but it usually involves oxygen. So don't include these oxygen in the total oxygen count. So on the left side, there's just 3 oxygen, not 7. So balance the larger molecules first. Leave the single atoms until last, the elements until last. And so I got a 3 there. So I'm going to say, let's put a 3 in front of over here, because that gives me the 3 sulfates, but then I've got to put a 3 in front of this because now I need more hydrogen. So that kept that the same. But now I also need more oxygen, don't I? The hydrogen is getting balanced, everything's getting balanced. So that's what you do. You start, you look at this, say I need, put a 3 here because I need 3 sulfates. But that changes the number of hydrogens, so I've got to put a 3 here so I have the right number of hydrogens. But that gives me 3 oxygens. Oh, I need 3 oxygens, so it's balanced. Is that okay, guys? You see the steps? Okay, that's it. We're done. Like I said, this is one that they developed for us, but it all kind of plopped out instead of coming through in steps. It does help, but it's not exactly perfect. All right, so whenever you're doing work in the future in kind of lab or whatever, quiz, show the work like this. Don't just, I'm gonna multiply by 3 to fix this or whatever. Show the work like that so we see the units. It's called dimensional analysis, or using these conversion factors. When you multiply by conversion factor, you multiply by 1, because they're really different units, but the same amount of whatever. Did you get one of these?
No.
You do not. This, let's get it back at the end of the year. Probably not using them yet in your class so much, but you can go ahead and open up the packages as you need. Maybe you can get use zip-up bags at home or something to kind of keep together. But the black is supposed to be carbon. They have a color code, and there's a color code in there. I don't always follow that because I like to always use carbon, because then I can show the double bonding and everything, and the shape of the molecule comes out right. So those are handy, but right now that's not what we're doing. So did everybody get one of these? I pass these out, right? Okay. All right. So I think let's go back because we're just about ready to start the lab. Let's see. So you understand the mole ratios is based on what in a reaction, chemical reaction, guys? The mole ratio, the number of moles, pardon?
The coefficients.
Of what?
The element. The products and reactants.
Right. You guys aren't real familiar with all terminology yet, that's fine. But the balanced chemical reaction. So you can write a reaction up there that's not balanced. So you need it. Once you balance it, then the mole ratio depends on the chemical reaction and what's balanced. So, good. Use this guy, it should help. Okay. For this lab, we're doing lab experiment 4. Is that right? Okay. Let's get ready to get started on that.